This is Captain Chaudhari in my series of videos on basic ship stability calculation under the topic of bilging. I want to do now bilging calculation involving the list, where one of the side compartment gets bilged on a box vessel and we will find out the list. So I've taken this question from my book on ship stability. There is this box vessel 140 meters by 21 meters. So this vessel is 140 meters long and it's 21 meters in breadth. It has got a midship compartment of length 18 meters and the midship compartment of length 18 meters is further divided longitudinally into port, starboard and center compartment. Port and starboard compartments are 6 meters in breadth and the middle compartment is 9 meters. kg of the ship before damage is 7.5 meters. Right? You are supposed to find out the list once a port side compartment gets bilged. Cargo therein has got permeability of 70%. We need to find out the list and we also need to find out the drafts on the draft amidships on port and starboard side. So as usual, we will first find out the loss buoyancy. Loss buoyancy is equal to length of the compartment, that is 18 into 6 into the draft of the ship was 7.2 meters into permeability, that is 0.7. So let us see what is the loss buoyancy. It is 18 into 6 into 7.2 into 0.7. That gives me 544.32. 544.32 meter cube. So that is loss buoyancy. Okay, intact water plane area is total minus lost water plane area. Total water plane area is 140 into 21 and lost water plane area is 6 into 18. But the permeability is 70%, so multiply by 0.7. So 140 into 21 equals minus, in the bracket you have 6 into 18 into 0.7, bracket closes. I get 2864.4. 2864.4 meter square. So 544.32 is the loss buoyancy divided by intact water plane area 2864.4. That gives me 0.190. Sinkage is 0.190. So I'll make a note of intact water plane area. It's 2864.4 and sinkage is equal to 0.19 meters. So the new draft is 7.2 plus 0.19, so 7.39 meters. And because it is a box vessel and damage is vertically uniform, we can say that half of this, half of 7.39 is the new kb, that is 3.695 meters. That is the new kb. If we look at the plan view of the ship, looks like this. Side compartments are 6 meters and the middle compartment is 9 meter in breadth. This is the center line of the ship. Original center of flotation is over here. If we say that this is the port side and port side gets damaged, what happens is the center of flotation would shift away from damage and this becomes the new line whereabout the ship will roll, or get listed. So if this is F, this point is F1. So we need to find out FF1. To find out the FF1, we have the same strategy. We take the moment of the whole area about the center line. So distance will be 0 because the distance from centroid to the reference axis is 0. So A into 0 minus the dimensions of the damaged compartment, that is 6 into 18, and what is the distance up to the center line? 4.5 plus 3, that is 7.5. But the permeability is 70%, so multiply by 0.7. This is divided by intact water plane area, that is 2864.4. This will give me FF1. So FF1 is 6 into 18 into 7.5 into 0.7. This is divided by 2864.4 to give me FF1 as 0.198. 0.198 meters is the FF1. Right. So the center of flotation has shifted on the starboard side because the damage is on the port side. After finding out FF1, we also should be finding out what is BB1. But please note that if we look at the construction of the ship, the damage is vertically uniform, and because the damage is vertically uniform, we say, suppose we assume that this side is port side and this is the damaged compartment. Can we say that the spread of the compartment or the damage itself is vertically uniform? The shift of center of flotation, because there is no double bottom, the shift of center of flotation should be same as shift of center of buoyancy. So BB1 also will be 0.198. Now we need to find out what is the BM. And to find out the BM, we need to find out what is the residual moment of inertia about this new fore and aft axis. So to find out the residual moment of inertia about this new axis, what is the moment of inertia, the total moment of inertia about this new axis? Total moment of inertia about the new axis would be 140 into 21 cube divided by 12 plus 140 into 21 into 0.198 square. This is the total moment of inertia about the new fore and aft axis. From this we need to minus the lost moment of inertia. Lost moment of inertia is, first of all, what is the moment of inertia about own axis, that is the damaged compartment axis. So that is 18 into 6 cube upon 12. Now what is the moment of inertia about this new fore and aft axis? So the distance to the new fore and aft axis is 7.5 plus 0.198, right? So that is 7.698. So 18 into 6 cube upon 12, that is the moment of inertia about the own axis, and if we need to transfer it to the new fore and aft axis, it will be AD square. Plus AD square means 18 into 6 into 7.698 square. Now the loss is not 100%, the loss is only 70%, so this whole thing has to be multiplied with 0.7, and this quantity is to be subtracted from total moment of inertia. And once we have the residual moment of inertia about the new fore and aft axis, this will have to be divided by intact underwater volume, and intact underwater volume is 140 into 21 into 7.2. So let's solve this. 140 into 21 into 21 into 21 equals divided by 12 equals plus, what we get is 108,160. So what I get is 108,160. 0.3 we can write. Actually, the decimal can be omitted. The digit after decimal can be omitted. Let's solve this part now. 18 into 6 into 36 equal divided by 12 equals plus in the bracket 7. That gives me 4706.79 minus 4706.8. Okay, this divided by 140 into 21 into 7.2 will give me the new BM transverse. This is BM transverse. Residual moment of inertia about the center line or the 4.5 axis passing through the new center of flotation divided by intact underwater volume. So let us solve this now. 108,160.3 minus 4706.8 equals divided by 140 into 21 into 7.2 bracket closes 4.887. So this is 4.887 meters. So that is the BM. We know the kV as 3.695. So what is the km? Km transverse is equal to plus 3.695 gives me 8.582, right? 8.582. If I minus the kg, kg is unchanged, 7.5 meters. So I subtract 7.5 from this, I get 1.082. The GM transverse is 1.082. So I have GM transverse as 1.082 meters. I have the BB1 as 0.198. The list that is caused is given by this expression: tan theta is equal to GG1 upon GM transverse. In this case, we can take BB1 because for equilibrium, BB1 should be equal to GG1 approximately, divided by GM transverse. So BB1 is 0.198 and GM transverse is 1.082. So let us find out theta. 0.198 divided by 1.082, shift tan gives me 10.37 as the list. Theta is equal to 10.37 degrees. So when we look at the ship, the transverse section of the ship, now this breadth is 21 meters. A simple geometry will tell you if the damage is on the port side, the center of flotation would shift on the starboard side, and the new water line compared to the old water line, they will intersect at this point, the new center of flotation. So can we say that this side is 10.302 and this side is 10.698, because compared to the original distance 10.5 meters, the shift is 0.198 meters. So can we say that the opposite side is tan theta of this, or opposite upon adjacent is equal to tan theta. So we say on the starboard side, the decrease of the midship draft compared to 7.39 is 10.302 into tan 10 degrees 10.37 degrees. And same way, increase of draft on the port side is 10.698 into tan of theta. Theta is 10.37 degrees. So we get the final drafts on starboard side as 5.505 and on the port side 9.347 meters.